Hi juniors, how are you? Now we have a different title or different topic for our pre-labs, and actually very important one, which is complex formation titration or complexometry or complexometric titration. What is complexometric titration? The volumetric methods involve reaction of metal with a ligand to form complex. We have used in acid-base titration, we react acid with base, but in complexometric titration we react metal with a compound called ligand. We consider ligand as a Lewis base and the metal as Lewis acid. And the formed bond between them is called coordinate bond. So, the complexometric titration is the acid-base reaction according to Lewis, where the ligand is a Lewis base and the metal is a Lewis acid. So the pH of the medium need to be adjusted, and we use indicator to show the reaction complete and to know where is the end point. Every metal have a high tendency to form complex even with water. The metal complex with water called aqueous complex. When we start titration, put few moles from the ligand replace the water to form stable complex with the metal, which means the metal complex is more stable than the aqua complex. So the term of stability must come with a constant which is called stability constant or K. What is K or stability constant? Is an equilibrium constant for the formation of a complex in solution, or a measure of the strength of the interaction between the reagents that come together to form a complex. So, when the stability constant increase, the tendency to form the complex increase, right? So, that means that the stability constant of the ligand metal complex is more than that of the aqua complex. Okay, so it easily replace it when we start to add the ligands. Ligands have different definitions. Either complexing agent, which almost form complex, any compound, any ligand forming complex called the complexing agent. Okay, if the formed complex is the form ring, is a form of ring, either soluble or insoluble, it's called chelating agent. And if the formed complex is in form a ring and soluble, it's called sequestering agent. Okay, if either ligand start, the big title is complexing agent, subtitle is chelating agent, subtitle is sequestering agent. Sequestering is a soluble ring complex. Chelating is a complex in form of ring, either soluble or insoluble, and most one is a complex form, complexing agent of which form complex. And depending of the number of the binding sites, if we have just one bond, it's unidentate. Two binding sites, the bidentate. Three binding sites, tridentate, and more than that is called polydentate. The most common used ligand is ADTA, which is isolene diamine tetraacetic acid disodium salt, soluble form of ADTA. This name is very important. You must study and memorize it. It have a symbol of Na2H2Y, which is also a sequestering agent. If you see the structure here, you'll see that the metal form 6 bonds with ADTA. You don't have to memorize the structure, it's just to know it, to see it. So 6 bond means it's a hexadentate, polydentate, or we can also say hexadentate. It reacts 1 to 1, which make it easily for the calculation of the F capital. If you saw the equation there, we say the metal is M, have a number of positive charge N positive, and the symbol of ADTA is H2Y and 2 negative charge. React by removing the H or replacing the H. Metal replace the H atoms present in the ADTA sample. So it My n minus 4, and the number of positive charge on a metal, either 2, 3, or any numbers. Okay, minus 4. For example, here if we have a metal with a 2 positive charge, it will be a formic complex like My have charge of n negative n negative 2, sorry. So again, if we have a metal with two positive charge, so n positive 2 minus 4 will be negative 2. Okay, if you see here, the arrow have two heads, which means a reversible reaction, and it gives two H positive, two hydrogen atoms, which means that we need an alkaline buffer to make the reaction go forward and capture the hydrogen atoms released. Okay, what is the advantage of Reactita? It is cheap, available, react with most metal, and form stable complex with most metal too, reacts in ratio 1 to 1. What is the disadvantage? Its reverse reaction require using alkaline buffer as we discussed before, and is non-selective, which means it reacts with most of metals, so we don't have for it a ligand or a complex metric reaction for every metal. Okay, it is a secondary standard due to presence of impurities from the industrial senses, so we need to make a standardization for it. Why we use alkaline buffer in complex metric titrations? As we see before from the equation, it's a reversible reaction, so by adding alkaline buffer it captures the H and the reaction goes forward. Also we use an indicator. Indicators we use in the complex metric titration can be also used in acid-base titration, so to make the color change only at the end point due to change in metal concentration, not due to the pH change. We use a buffer to stabilize pH. Okay, so we can know the end point at the end of the last ion metal. So what is the indicator can be used in complex metric titration? It's called metallochromic indicator. Term metallo come from metal and chromic come from color, which is a color complex formed with metals. We have three examples. First one is EPT or aureochrome black T or solochrome black. We have to memorize these names too. Second one is peroxide, which is ammonium salt of pipeриc acid, and third one is xylenol orange. The metal indicator complex have a color, and the free form of the indicator have a different color, so at the end point we will see the color of the free form. What is the requirement of successful use of metal indicators, or when to say that that indicator can be used as metallochromic one? First one, the indicator is not necessary to be specific but at least selective, which means we don't have a specific indicator for each metal, but at least sometimes we can use an indicator to differentiate between two metals, and we will have an example about that in the next pre-lab. Second one, the must that the metal editor complex is more stable than the metal indicator complex, so it will be able to displace it from the metal complex, right? Otherwise we can see the end point. Also, the metal indicator complex must be of sufficient stability, not to be versatile or not stable. That must be of sufficient stability. And the indicator free color could be easily differentiated from the metal indicator color. To distinguish the principle or to understand the principle, let's see that diagram. From the beginning, we have a metal dissolved in water, so it formed metallic aqua complex. When we add a small amount of the indicator, part of it form a metal indicator complex. Then when we start the titration, the additive will replace further the water and form metal additive complex. Then at the end point, it will replace the indicator and we can see the free indicator color. During complex metric titration, we must do vigorous shaking with rapid titration. Why we need vigorous shaking? To be able to dissociate the aqua complex, and the indicator can be increased anytime during titration. If you can see that the color come lower, you can see enough, so you can add more. And that's important. Once the endpoint is reached, the color doesn't change, which means that you can come to us and say, doctor, is that color is right? Yeah, it's right, but I don't know if you have put more melons or not, because once we have the free indicator color, that nothing will change. First example we have today is zinc sample. What's the principle of zinc sample? Zinc informing zinc sulfate directly titrated against adita in presence of ammonia buffer pH 10, that's important, and using a PET as indicator. The zinc APT zinc APT complex has a violet color, and the free form of the APT is full blue. So at the beginning we will see violet color, and at the end point it will be full blue without any tinge of violet. What is the equation? When first zinc APT is present, and when EDTA at start titration, EDTA will replace APT, and we can see the free color indicator. From the beginning we have zinc forming aqua complex with some of zinc forming the color violet with APT. During titration the zinc aqua complex will decrease, and the end point that EDTA will replace the APT, and we can see the full blue color, the free form of APT. What's the procedure? We will take 10 ml from zinc sample, add 2 ml ammonia buffer, and add few specks of APT. The color will be violet. Few specks mean small amount, like when we add salt to our food. Then the endpoint would be full blue. Record the mLs from the burette and go to the calculation. As we know that EDTA react 1 to 1 with the metals, we can easily calculate the F capital, test yourself, and compare it with our results. Then the concentration equation will be mLs times F small times F capital times 1000 over the 10, which is sample volume. Second example would be the nickel sample. Nickel directly titrated against EDTA in presence of ammonia buffer and pH against 10, and using meroxide as indicator. A meroxide nickel complex is yellow color, and the free form of meroxide is purple, as easily distinguished. When we add EDTA to the nickel indicator complex at the end point, it will replace the indicator and the color change to purple. Here again, the beginning, nickel is forming an aqua complex with water, and some of nickel is combined with meroxide forming yellow color. So during titration, EDTA replace water, and then during or completing the titration at the end point to replace that meroxide, and we can see the violet color. What's the procedure? We add 10 ml of nickel samples to 2 ml of ammonia buffer, then few specks of meroxide, and the color will be yellow. Then titration with 0.1 EDTA, and the end point is purple. And as we know from the calculation, nothing had changed. Third one is copper sample. Copper principle is very important and very interesting too. It's direct complexometry involved that copper directly titrated against EDTA in presence of diol ammonia using meroxide as indicator, and the end point is purple. Actually, copper is alkaline medium form copper hydroxide percepted. So at the beginning, when you start to add the ammonia, you will see a white percepted form. So when you add more ammonia, this percepted will dissolve and form a copper amine complex, which is soluble and have a blue color. So at the beginning, when you start to add the ammonia dropwise, you will see a white percepted, and adding more ammonia till the this percepted is dissolved and have a blue color, which is copper amine complex. Then when you add a meroxide, copper meroxide is yellow, so the yellow with blue form green. You will see like an olive green color in the flask. Then when you start to add EDTA, the copper amine complex will be replaced first, so the EDTA will replace amine or the NH3. And you will see during the titration that the color gets lighter, and you can see somewhat yellow color. And at the end point, you'll see the color of the free indicator, which is purple. So when you ask you what is the role of dial ammoniate, it's auxiliary complexing agents form copper amine complex and also gives a suitable pH for formation of copper adita complex. What is the procedure? Add 10 ml copper sample, then dial ammonia dropwise till the formed PBT is dissolved into copper amine complex with blue color. Then we add few specks of meroxide and we will see the flask transform it to dark green color. Then we start titration with 0.01 molar edita and the endpoint will be purple. The calculation as we use nothing changed and the last sample is lead sample. Lead also direct complex metric titration, titrated against added and presence of hexamine, which pH is 5 to 6 using xylitol orange as indicators. It's important. Buffer actually hexamine when you ask you why you use hexamine, because the pH is more stable for the lead edita complex. Okay. At the end, before the end point, when you add iron orange, it will form the violet red, which is a metallized form color, and the free form is yellow. Again, why pH 5-6 the most preferred here, because it gives maximum stability of lead edita complex and increase selectivity. The type how to increase selectivity. What's the procedure? Add 10 ml of lead sample, 2 ml of hexamine, 2 drops of xylitol orange, and you will see violet red color in the flask. Then titrate it with 0.01 molar edita and the end point will be yellow. The calculation as we have used before, nothing also changed. Every time try to train yourself in F capital because it's very important. Thank you. Good luck.